Now next come to the next three properties. The first one says that if you have two unsigned or complex measurable functions f and g, so they are either unsigned measurable or complex measurable, then the sum and the pointwise product are pointwise sum and pointwise product are unsigned measurable or complex measurable. So because complex measurability depends on real measurability and which further depends on unsigned measurability, so it suffices to show the unsigned measurable case and the complex measurable case will follow. And here we can simply write, for example, f plus g, and if you take the set f plus g greater than some constant lambda, then this can be written as the union of the sets f greater than some number q intersection f g then should be greater than lambda minus q, and if you take q to be the rationals inside the extended reals, then you get a countable union and each one of them is of these sets are measurable. So these are all measurable sets because f and g are measurable, and so therefore f plus g is measurable. Now for the second part, for the pointwise product, first let suppose that f equal to g. So if we can prove that f square is measurable, then the pointwise product of f with itself is measurable. Then we can deduce that f g is measurable. I will show you how. So first suppose that f equal to g, and then we can write f square greater than lambda, this set is equal to f greater than square root of lambda. So because lambda is a non-negative real number, the square root is unambiguously defined. So this is measurable. So this is measurable, and so f square is measurable. And now you can write f g as, you can use the following formula, f plus g whole square minus f minus g whole square. And so first that the sum is measurable, then the square is measurable, and the sum, again this is a sum of two now no longer unsigned, but nevertheless you can view it as a complex valued measurable function, and then you can take the square, and so these are all measurable, and so the whole thing is measurable. Of course the multiplication by a scalar does not affect measurability as well, so this is measurable. So this is the sixth part, sixth part, this is 7 and this is 8. And now if you take the seventh one, for example, if you take the supremum, so you can take g greater than lambda as the union n greater than or equal to 1, and then you can take fn greater than lambda. So the supremum greater than lambda means that at least one fn must be greater than lambda, and the reverse inclusion is obvious. So we have this equality when g is the supremum, and similarly if you take h, then h is minus the supremum of minus fn, and so again we are reduced to the case of supremum of no longer unsigned but still complex measurable functions, and so we have h is also measurable. So both supremum and infimum are measurable functions. Now lastly, if you have a pointwise limit of measurable functions, each fn is unsigned measurable, then f itself is unsigned measurable. So let's see why this is true. This is again simply because fx is the limit as n goes to infinity of fn x for each x. We have this formula, and the limit is precisely well defined when you have equality of the lim sup and the lim inf. So, this is the lim sup in particular of fn x, which is infimum over k of the supremum of n greater than or equal to k fk fn x. So, again this part is measurable and this part is also measurable. So, the whole thing is measurable, f is measurable. So, we see that we can deduce many properties from the basic properties of measurability. Now, let me define what are simple functions. So, function s from x to the non-negative extended reals is called a simple function if the range of x takes on finitely many distinct values alpha 1, alpha 2 up to alpha n. So, of course, we have the immediate remark that s is unsigned measurable if and only if the sets ai, which are the pre-images of these values alpha I, are measurable for each I. Each I in 1 to n. So, if your s, if the function s takes a constant value alpha I on a measurable set ai, and your x can be written as, so of course here x can be written as the union of I equal to 1 to n ai then. So, if x can be decomposed into measurable sets ai finitely many such that ai, so sorry, this as simple function we do not allow it to take the value plus infinity. So, it is only defined for real non-negative real numbers, but not the extended real numbers. So, we only allow the sets ai where sx is a finite real number from 0 to infinity. Then this sets are measurable and x can be decomposed as a union, finite union of these ai's. In fact, they are going to be disjoint because alpha i's are distinct. So, these are very much like the piecewise constant functions that we have dealt with when we were defining Riemann integrals. There we had boxes, the piecewise constant function took on a constant value over a partition. The partitioning was for boxes only, but here we are allowing partitions with with measurable sets ai, and then it's more or less the same definition as a piecewise constant function. So, a simple measurable function is very useful in measure theory because of the following lemma, because if f is an unsigned measurable function, then there exists a sequence Sn of measurable function, of simple measurable functions such that first part is that it is an increasing sequence of non-negative measurable functions, and bounded above by f, and the second part is that the limit of these measurable functions is precisely the function f. So, Sn converges to f pointwise on x. So, this kind of result says that any measurable unsigned measurable functions can be approximated by simple measurable functions. So, let us see the proof, or rather the sketch of the proof. So, first of all, define functions phi n from 0 plus infinity to 0 plus infinity as follows. So, we define phi n of an extended real number t if 0 is less than or equal to t is less than or equal to some is less than or equal to this n, where n is this index here, then we can find a natural number k such that k over 2 to the power n is less than or equal to t is less than or equal to k plus 1 by 2 to the power n, and in this case we write it this as k. So, for each t in this interval 0 to n, less than n, we find an interval. So, we subdivide this interval 0 to n into equal intervals of length 1 over 2 to the power n, and our t will lie in one of these intervals, and we find this index k such that k by t to the power n is less than or equal to t is less than or equal to k plus 1 by 2 to the power n. So, we are taking this value k here where t lies between k by 2 to the power n and k plus 1 by k plus 1 by 2 to the power n. And then if t is greater than or equal to n, we just set it as n. So, first note that phi n inverse of a Borel set in 0 plus infinity is a Borel set in 0 plus infinity. In other words, phi n is a Borel function. Phi n is a Borel function. And secondly, that for any t, and so t in 0 plus infinity and n greater than or equal to 1, we have the inequality t minus 1 by 2 to the power n is less than or equal to phi n t is less than or equal to t, which means that as n goes to infinity, phi n t converges to the function identity function t. And thirdly, that if we set Sn of x is equal to phi n of fx for x in x, then this is the sequence of functions that we want. This is a simple function because it can be written as a sum k equal to 1 to n times 2 to the power n. Here n times 2 to the power n is the number of subintervals that of length 1 by 2 to the power n that we are dividing into for the set 0 to n. So, we have k equal to 1 to n times 2 to the power n of this value k over 2 to the power n. So sorry, this should be k over 2 to the power n, and then you are multiplying by the indicator function of the inverse image of precisely these intervals k by 2 to the power n, k plus 1 by 2 to the power n. So here again there should be a strictly less than sign. So these are all Borel sets. So these are all measurable functions. The indicator functions are all measurable functions, and plus you have n times chi of the set n plus infinity. So this is a finite sum of indicator functions of measurable subsets of x. So this again should be f inverse of n plus infinity. So these are all measurable, these are all measurable, and so these are this Snx is a simple function, and it's easy to show that Snx is less than or equal to Sn plus 1x. So this proves part A, and the limit of Snx as n goes to infinity is equal to the limit of n goes to infinity phi n of fx, and this is precisely equal to fx as phi n t converges to the identity function t.